Hello. Today I'm going to explain something called the national grid. And the national grid is the system of wires and pylons that gets electricity from the power station to your house. It's very, very long. And it's very, very easy to lose lots and lots of energy along the route, along those hundreds of miles of wire. So they have to put a few systems in place to make sure it doesn't happen. Let's have a look. Okay. This is a power station. Okay, it's a power pack, but we're pretending it's a power station. And what we've got here is the DC, the direct current. It's coming straight out of the power station and it's going into this bulb, which is lovely and bright. That's about 8 volts. And then that energy is going into wires. It's running into these wires, which this is just a couple of meters long, but in the national grid it will be hundreds of miles long. If we go along here, and it follows on all the way along here. They're getting warm. I can feel a bit of warmth there, and it's getting warm, and energy is being lost. And the energy and the current flows down here, and we get to the far end, we get to the house. Now this house is a problem. It's very dim. Lots and lots of energy has been lost. We turned all that energy into heat, it's been lost, and now we've just got a very dim house. That's no good. What we need is a system where somehow, magically, that energy does not get lost. The first things I'll be showing you are these things here called transformers. Transformers change the electricity. Let's have a look. This is a transformer. I'm going to have to set it up in the right way round. It's going in at this side here, which doesn't have many coils. I'll explain what those are all about in a bit. I'm going to put that in on that side. This is called a step-up transformer, and what it does is it increases the voltage. It makes it so it's got a greater voltage, and so that along these wires we have a really, really high voltage current flowing. And then, when it comes down here, you will see that there is no light at all here. There is no light. And what we have is another transformer, which is just the same really, but it's connected the other way around, and it is what we call a step-down transformer. So I'll put the step-down transformer in. Now you will notice, although I've added a step-up transformer and a step-down transformer, there is no light. Let's have a look along here. We did have light here. We've got some sort of energy being generated at this end. Nice and bright. Step-up transformer, long cables, step-down transformer, no light. It would appear this is not a very good system at the moment. Well, there's something else they have to do. And the other thing they have to do is they have to use a different sort of electricity. This is DC. DC means direct current, and it means the electricity goes all the way along and then all the way back again, and then all the way along and all the way back again, just like you'd imagine current. Things are different though if we use AC. AC is alternating current. And if we look on this alternating current, the electrons don't actually go anywhere. The electrons don't move, they just go backwards and forwards and backwards and forwards and backwards and forwards. And the ones here go backwards and forwards, and the ones here go backwards and forwards, and the ones here go backwards and forwards, and the electrons here go backwards and forwards. 50 times a second, backwards and forwards and back, and all the way down here. They're not really going anywhere, but they're just vibrating backwards and forwards. They go into the step-down transformer, and when they come out at the far end, you will see we have a nice bright light. So, if you don't want to lose energy, what you need is a step-up transformer and a step-down transformer, but you have to be using AC. It doesn't work with DC. I can actually feel that vibrating. That's actually vibrating quite a lot. Feels a bit crazy. That's because it's AC. It's changing direction 50 times a second. Some people say, that's a bit weird, sir. How come it is you put electricity into here, and then this increases the voltage? Where has that energy come from? Where has those extra, suddenly loads of extra volts come from? Well, it has changed the voltage. It's increased the voltage massively, but it reduces the current, which is a bit weird. The electricity is carrying more energy, but there's less electricity. Again, all the way along here, it's a higher voltage, but there's less current. So actually the energy is the same. High voltage, low current, but the energy is the same. High voltage, low current, but the energy is the same. When it comes down to the far end, it's reduced and it gets made safe. This makes it so it's a safe current, so you don't get blown up. If you get a shock at home, it hurts. It's low voltage, but it still hurts. If you get a shock here, in real life, you would be dead. This is something like 500,000 volts. Let's step it up to 500,000 volts. So, just to summarise, power station, making plenty of electricity. Power station is putting out alternating current. Step-up transformer, extremely high voltage, but low current. Step-down transformer, house, no energy has been lost. That is how the national grid works. You've got to have transformers and high voltage and alternating current.